Okay, this is the 6th video for IB Astrophysics. Last video we looked at the life cycle of a star. Protostar collapses into a main sequence star, which fuses hydrogen into helium for billions of years, and then when it runs out of hydrogen in the core, it turns into a red giant, which burns helium into carbon, and then when it runs out of helium fuel, it forms a planetary nebula and a white dwarf, which then gradually cools off until it turns into something called a black dwarf, which is essentially a giant lump of charcoal floating out in space. A larger star, meaning 5 solar masses or greater, certainly 10 solar masses or larger, when it runs out of hydrogen or helium in the core, what happens is it'll collapse again, shrink again, temperatures will go up even higher in the core, and the result is that it can undergo carbon fusion. And what happens is you've got helium and carbon fuses to form oxygen. And then oxygen and carbon fuse to form silicon. And from there, very, very interesting things happen that are complicated and you don't need to know. But eventually, you end up with iron. If you recall from our nuclear unit, iron, specifically iron 56, has the highest binding energy of any nucleus. And that means that once you get to iron, fusion can't go anywhere. So once you have iron, fusion basically stops. And now you've got a problem, if you're the star. What's happening is fusion in the core has stopped. That means no more radiation pressure. But the core is also made mostly of iron, which means it's very, very dense, and there's lots of gravity. And so you have lots of gravity, suddenly no more radiation pressure. What happens is the core collapses. What happens is electron degeneracy pressure is no longer able to hold the core up against gravity. And you get what's called a core collapse supernova. Essentially, the star explodes. It's very violent. A shock wave goes through the star in a few seconds. Keep in mind that the star is a red giant at this point. Its radius is larger than the distance from the Earth to the Sun. For a shock wave to travel through it in a few seconds, that shockwave has to be moving at basically the speed of light. And temperatures are extremely high in the shockwave, with the result that elements heavier than iron are formed instantaneously. The star can release more energy in a few hours than it did in multiple millions of years as a main sequence star. And a supernova is one of the brightest things in the sky. For instance, if a star like Sirius A were to undergo a supernova right now, even though it's 10 or so light years away from Earth, it would be as bright as the sun in the sky and would probably have really, really terrible effects on life on Earth. Fortunately, it's not going to do that anytime soon because it's not a red giant. But supernovas are really cool, they're very violent, and fortunately they generally happen very far away from Earth. And what's left behind after a supernova is usually a neutron star. And what happens with a neutron star is that when the core collapses, the electrons on the atoms get pushed down onto the nucleus. And essentially what happens is reverse beta decay. You get electron capture. Electron eventually runs into a proton, and the two of them form a neutron. So electron plus a proton gives us a neutron, and then in order to keep the lepton number conserved, a neutrino has to come out. And so essentially what you have is a huge, huge nucleus. It's just entirely composed of neutrons, although it has an outer shell of carbon, or of iron, and it's held together by gravity. And typically these neutron stars spin really rapidly because remember that most stars were spinning before they exploded, and all of a sudden the mass of a star, which is spread out into a sphere of radius 1 AU or so, gets compressed into a radius of a few kilometers. And so what happens is they start spinning really rapidly, and when we say rapidly, we mean thousands of times per second. It's kind of like a skater pulling his or her arms in. You speed up, but more so. And some of these neutron stars emit beams of radio waves. We're not totally sure where those radio waves come from, but here's the neutron star, and it's spinning around this axis. But the radio waves come out of two opposite points on the star, and as it spins around, those beams rotate in circles as well, and it's kind of like the light on a fire truck. You see flash, 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 flash. They're called pulsars because they have regular on-off, on-off, on-off radio waves, and when they were first discovered, people thought they were aliens sending Morse code, but they weren't. So what you need to know is what happens to a large star. It burns, fusion happens up to iron. At that point, the star explodes in something called a supernova, leaves behind a neutron star. Or, sometimes, for really big stars, turns out that neutron stars can only be so big. If the neutron star has a mass of greater than 3 solar masses, we call that the Oppenheimer-Volkoff limit, it cannot support itself against gravity, and neutron degeneracy pressure goes away, it collapses further, and as far as we know, it collapses to a geometrical singularity, and surrounded by an event horizon, we have something called a black hole. And black holes are weird, we don't know a whole lot about it. You just need to know that a star that is too big to form a neutron star will eventually collapse into a black hole.